Hello, everybody. All right, so today we're going to get started with section 311, dealing with related rates. So I'm going to get the file up here. All right, so our objective today is going to be to um, talk about what related rates are and how to find related rates, and then how to use related rates to solve real life problems. So for an example here, now, within related rates, we're going to be using two parts of differentiation, the chain rule and implicit differentiation. And we're going to be looking at finding the rates of change of two or more variables with respect to time. So for an illustration, let's say, for example, we have a square whose side length is increasing at a rate of 1 centimeter per second. And we want to know how fast the area is increasing. Now, of course, we would expect that the area is going to increase as the length of the side of the square increases, because obviously the larger the side of the square, the larger the area is going to be. So in this illustration here, we can see at various times, assuming that the side length is increasing at 1 centimeter per second, at 1 second, the side length will be 1 centimeter, 2 seconds, side length is 2 centimeters, 3 seconds, the side length is 3 centimeters, at 4 seconds, the side length is 4 centimeters. And so here we have a rate of change, a rate of increase of the length of the side, which is equivalent to 1 centimeter per second. So we can call that dsdt using the um, derivative notation, dsdt here. Now, if you look at the area of each of the squares, though, at the first second, when the side length is 1 centimeter, the area is 1 square centimeter. That should be a square centimeter there, so that's a typo on my part. For 2 seconds, the area is 4 square centimeters. After 3 seconds, it's 9 square centimeters. And after 4 seconds, it's 16 square centimeters. Now, the interesting thing here is that we can see that obviously as time increases, the area increases, but the increase of the area isn't linear like the increase of the length of the side. It does increase, but the increase is not proportional to the length, the change in area isn't proportional to the change in the length of the side. What we see is that the area is actually increasing faster as the side length increases. So it seems here that the rate of change in the area depends on two things: the rate of change of the side length, as well as the length of the side at any given time. So now question, how can we determine the rate of change of the area, which we'll call dA dt, in this problem? Well, four things we need to know. First, we need to know how fast the side length is increasing. Secondly, we need to know how big the square is at the time we're measuring dA dt. Thirdly, we need to know the general relationship between the side of the square and its area. Now, basically what that means is that we just need to know the formula for finding the area of a square given the side of a square, which we know, and we'll get to that later. And then we need to know how to differentiate, because if we're trying to find rates of change, those are that's derivative speak right there. So let's say we want to know how fast the area is increasing, dA dt, given that the side is increasing at a rate of 1 centimeter per second. So ds dt is going to be 1 centimeter per second, when the side of the square is 3 centimeters. All right, so for that, we're going to take a look at we're going to move on to a whiteboard here. So give me just a second. All right, so the first thing we need to know was how fast is the side length increasing? So we have that already. So ds dt, that was equal to 1 centimeter per second. The second thing was how big the square is at the time that we want to measure the change in area. And in this case, that was the side length, which was equal to 3 centimeters. The third thing, we need to know the general relationship between the side of the square and its area. So that's just the area formula for a square. So the area of a square is given by the formula A equals S squared. So it's just the length of a side squared. And then we need to know how to differentiate implicitly. All right, so what do we do at this point? Well, remember, we're trying to find, our goal is to find dA dt. So then what we do, we begin with the area formula of a square. A equals S squared. And then we will differentiate this with respect to t. Now, since t is not a variable that's in the equation, we're going to be using implicit differentiation here. So we know that the area and the length of the side are both functions of t. So when we differentiate them with respect to t, we'll have to have basically that that notation for differentiating with respect to t. So if we differentiate both sides of this equation, well, the derivative of a, is just equal to 1. So this will be 1 times dA dt. On the right side, s squared, derivative of s squared, that's going to be 2s times ds dt. All right, so remember we have those notations because we're differentiating with respect to the variable t. All right, so now that we've differentiated both sides, notice we have that notation. We have dA dt, ds dt. Remember what our goal is. Our goal here is to find dA dt, and in this case, we already know what ds dt is. So what we can simply do is take our given information and plug it into this relationship here. So we have dA dt equals 2s. Now here s was equal to 3. So it'll be 2 times 3 times ds dt, which is equal to 1. So we multiply those together, that's going to give us 6. And so therefore dA dt is going to be equal to 6. Now remember, this is a measure of area. So the proper units here would be 6 square centimeters per second. So at the time that the square has a side length of 3 centimeters, the area is increasing at a rate of 6 square centimeters per second. Now, of course, the rate of change, dA dt, is going to be different depending on what the side length is. And so the answer is going to vary depending on how big the square is and also how quickly the area or how quickly the side length is increasing. Right, but this is would be the answer to our question here. Let's take a look at another example. Excuse me. All right, so now the file for that I'm showing this on, section 311, is available under your file, so you should have access to that. All right, so now let's take a look at the second example here. This example states that air is being pumped into a spherical balloon such that the volume is increasing at a rate of 100 cubic inches per second. Find the rate of change of the radius when the radius is equal to 5 inches. All right, so we have the same type of setup here. So now remember, what are the things that we need to know? We need to know how fast, we need to know the given information, we need to know the size at the time we're measuring, we need to know the general relationship, the equation or formula, and then we need to know some differentiation. So let's go back to this problem. All right, so now if we look at the problem, what we're given is we're given the rate of change of the volume. So we're given dV dt, which in this case is equal to 100 cubic inches per second. We want to find the rate of change of the radius when the radius is 5 inches. So they give us the radius value, which is equal to 5 inches. And we want to find the rate of change of the radius, which in this case would be dr dt. All right, so let's go back to the other screen. All right, so in this problem, we're given dV dt, which is going to be 100 cubic inches per second. And we're also given that the radius is equal to 5 inches. And our goal here is going to be to find the value of dr dt. All right, so we have the given information. We know what we want to find. So now we need to have a relationship between the radius and the volume. All right, so now this means we just need a formula to find the volume of a sphere. All right, now you may not know that formula, and that's, if you don't, that's fine. I will provide any obscure formulas that you may not know. Now, the volume of a sphere and pardon my handwriting here, is given by the following: V equals 4/3 pi times the radius cubed. Now, in all of these problems involving related rates, you're going to have some type of formula or equation that relates the variables that are in question. In the case of geometric shapes, it's pretty straightforward because you'll have, you're just looking for a formula. In some other problems, you may actually have to come up with the equation. So that might take a little bit of work. All right, so as you do the homework, if you get stuck with any of the problems, just let me know and we can discuss it. All right, so now we have our volume equation. So now, what's the next step? To use implicit differentiation to differentiate both sides here with respect to t. So on the left side, we have dv dt. Derivative of v is just 1 times dv dt. And on the right side, we'll have 4/3 pi. Now those are all constants, but now we're taking the derivative of r cubed. So that's going to be 3r squared times dr dt. Clean this up. We have dv dt equals 4 pi r squared times dr dt. And so now once we differentiate both sides, we see our derivative expressions dv dt, dr dt. And so now at this point, we just simply plug in our given information. So what were we given? We were given dv dt, which was 100 cubic centimeters. And that'll be equal to 4 pi, and r was the radius, and so this is 5 inches. So it's 5 squared times dr dt. All right, so now if we clean this up a little bit, we'll have 100 equals, the right side is going to be 100 pi times dr dt, and then divide both sides by 100 pi to isolate dr dt, and so dr dt will be equal to, would reduce down to 1 over pi. And so this is the rate of change of the radius, so that's going to be in inches per second. Okay, and we can approximate that with our calculators. So if we do that, 1 divided by pi, that's approximately 0.3. So 0.32 inches per second. All right, so with a constant change, with a constant volume change of 100 cubic inches per second, at the point where the radius is 5 inches, the radius is increasing at about 0.32 inches per second. Now, once again, depending on the radius is going to affect how large the radius is increasing. So a larger balloon would actually yield a smaller change in the size of the radius. Okay, so I hope that those two examples give you kind of a general idea of how we go about dealing with related rates problems. I want to end by giving you sort of a guideline for solving these types of problems. Okay, and that's going to be on the file here too. All right, so the basic steps here that are involved: 1, you want to identify all the given quantities and the quantities to be determined. Sometimes you might have to sort of draw a picture, make a sketch, and label the quantities. Second thing you want to do is write an equation that involves the variables whose rates of change are either given or need to be determined. Then third, using the chain rule and implicit differentiation, you want to differentiate both sides of the equation with respect to time, with respect to t. And then after you do that, you'll substitute into the resulting equation all the known values for the variables and their various rates of change. And then once you do that, you can solve for the required rate of change. All right, so that's the basic rundown for solving these types of problems. All right, so I'm not sure that I have enough time to do another example, so I'm going to stop at this point with the two examples here that should give you an idea of how to set things up. During our discussion time when we come together, hopefully we'll have an opportunity to do more examples if you want to see them take place, but hopefully this will give you sort of a rundown as to how everything works out. Okay, and as usual, if you do have any questions, when we come together as a group, we can address those questions and take a look at the homework problems in this section, in section 311, or in whatever the section number happens to be that deals with related rates. And if there's anything that you have questions on how to set up or how it might come together, just feel free to ask. So I hope to see everyone in class and, well, in our virtual class. And I'll see you then. Have a good one.